Good day, I'm James Mark Sumawang from BS Admetry A and I'm going to discuss my geometric model hexahedron. Hexahedron is a solid figure with 6 plane faces. I mark each face with capital letters A, B, C, D, E, and F, and each face has its corresponding movement. I name the group or the binary structure with capital letter H. So this is the figure I made so you can see what hexahedron really is. Okay, let's move on to the movement for each letter. So A, do nothing. B, turn the figure right. C, turn the figure left. D, the opposite. E, opposite then right. And F, opposite then left. So this time, let's proceed by filling the table of results of the set of H sub 6 under binary operation star. Do nothing and do nothing is still A. Do nothing and turn right is B. Do nothing and turn left is C. Do nothing and opposite is D. And do nothing and opposite right is E. Next, A star F is do nothing and opposite left F. Next is B star A, turn right and do nothing B. B star B is turn right and then turn right C. Next is B star C is turn right and turn left A. Next is B star D, turn right and opposite E. Next is B star E, turn right and opposite right F. Next, B star F, turn right and opposite left D. So next we have C star A, turn left then do nothing C. And C star B is turn left then turn right A. C star C is turn left then turn left D. Next, C star D is turn left and opposite F. Next, C star E is turn left then opposite right, opposite right D. Next, um, C star F is turn left then opposite left E. Next, D star A, opposite then do nothing D. D star B is opposite and then right E. Next, D star C is D, then turn left F. Next, D star E D star D is opposite, then opposite A. Next is D star E opposite, then opposite left, right rather, B. Next is opposite, then opposite left, C. Next, E star A is opposite right, and then do nothing, E. Next is E star B opposite right, then turn right, F. Next is E star C opposite right, and then turn left, D. Next, opposite right, then opposite, B. Next, E star E is opposite right, then opposite right, C. Next, E star F is opposite right, and then opposite left, A. Next, F star A, opposite left and do nothing, F. Next, F star B, opposite left and then turn right, D. Next is opposite left and turn left, E. Next is F star D, opposite left, then opposite, C. Next is F star D. Are we in D? F star D is opposite left, then opposite, C. Next, F star E is opposite left and then opposite right, A. Next, we have the last one, F star F is opposite left and opposite left, B.
Since we already got the table of results, let's proceed in our mission 1.
Mission 1. Show that the binary operation is a group.
So here is the table of results of the set of H sub 6 under binary operation star. Is it well defined?
Since the elements are clearly distinguishable and stated.
Yes. Is it closed? According to the table,
Since all the results in the table are all elements of H sub 6.
it is closed under binary operation star. Is it associative? Let's see. Let's rotate the table of results 180 degrees. And modify some row and columns. So first, interchange first and second column. Next, interchange fourth and fifth column. Then, interchange second and third row. And lastly, interchange fifth and sixth row. As you can see, the table we rotated is just the same as it is before. Therefore, the binary structure H sub 6 is associative under binary operation star. Next, we have to identify if the identity element exists. We must first find the row and column with A, B, C, D, E, F sequence in the table of results. Then find their intersection. In this case, the intersection A. So the identi element exists, that is, E is equal to A. Next, we have to identify if the inverse element exists for all elements in H. Since we already know the identity element which is A, we have to look for identity element in all rows and columns of each element. So for A inverse, it's A. B inverse is C. C inverse is B. D inverse is D. E inverse is F. F inverse is E. Since the binary structure H sub 6 under binary operation star is well defined, closed, it is associative, the identity element exists and the inverse element EXSRS for all elements in H, therefore the binary structure is a group.
Mission complete. Mission 2. Exploring its subgroups and cyclic subgroups.
This time we are going to explore the subgroups of H sub 6 under binary operation star. So first we have H sub 1 containing the identity element A, which is also called the trivial subgroup. Next is we have H sub 2, which contains the element A and D, a proper subgroup. And lastly, we have H sub 3 containing 3 elements A, B, and C, also a proper subgroup.
As you can see, the subgroups must have the same characteristics of a group. It must be closed, well-defined, associative, identity and inverse element exists. And there is also a subgroup called improper subgroup, that is the H sub 6 containing all the elements of H.
What you can see here is the lattice diagram of the set H sub 6 under binary operation star, which is arranged in improper proper trivial pattern, which means the improper subgroup in the top, which is the H sub 6 or the group itself, then in the second part in the middle, the H sub 3 and H sub 2, which is the proper subgroups. Then in the bottom part is the H sub 1, which is the trivial subgroup.
Next is the cyclic subgroups. Property 2, theorem. A subgroup of a cyclic group is cyclic.
So let's consider the subgroup H sub 2, which contains the A and D element under binary operation star of H sub 6. Then let's verify the closure property. D star D equals A. Then D star D equals D. So the subgroup AD is equal to the set of D is a cyclic subgroup of H sub 6 under binary operation star. Next, let's consider the subgroup H sub 3, which contains the elements A, B, and C under binary operation star of H sub 6, then verify closure property. So C star C is equal to B. So C star C is B, so B star C equals A. Then C star C is A. Star C equals C. So the set or the subgroup of ABC is equal to the set of C is a cyclic subgroup of H sub 6 under binary operation star.
Mission accomplished. Mission 3. Determining whether the group is cyclic.
Cyclic group. Definition. An element of a group G generates G and is a generator for G if the set A is equal to G. Group G is cyclic if there is some element A in G that generates G.
So now let's look for an element in H that generates H. Let's start with A. So A star A equals A. It doesn't generate H, so let's move on to B. B star B equals C. C star B equals A. Then A star B equals B. Still, it doesn't generate the group H, so let's move on to C. C star C equals B. B star C equals A. A star C equals C. So still not. Next is D star D equals A. A star D equals D. Still no. Okay. E star E equals C. C star E equals D. D star E equals B. B star E equals F. F star E equals A. And A star E equals E. As you can see, E generates all the elements in the group H. So one of the generators of H sub 6 is E. Next, let's move on to the last F star. F equals B. B star F equals D. D star F equals C. C star F equals E. E star F equals A. And A star F equals F. It also generates the group H. The generators of H sub 6 are E and F. That is the set of E and the set of F. So we can conclude that the H sub 6 under binary operation star is a cyclic group since we found a generator G for any A in H.
Mission complete. Mission 4. Relating order of the group and order of its subgroups.
Order of the group and its subgroup.
Consider the set of H sub 6 under binary operation star. The divisors of 6 are 1, 2, 3, and 6.
Let 1, 2, 3, 4, 5, and 6 corresponds to A, B, C, D, E, and F respectively. For each of these divisors, the set of H sub 6 under binary operation star has exactly one subgroup whose order is the divisor. We verify that by the following. As you can see on the list, the subgroup of order is based on the divisors of 6, which is the number of our elements in the group. So for example, we have in order 1 or the divisor 1, we have only one element in the set. In the order 2, we have 2 elements in the set. In the 3, we have 3 elements on set. And in order 6, we have 6 elements in the set. Therefore, we can identify the number of the subgroups and the number of the elements inside the subgroups by determining first the divisors of the order of the group.
Mission complete.